All right. Hi, everyone.
Hi. Insert here. We ran out of time. We were up all night. We were busting it all night getting everything ready, so this is what we came up with.
Yeah. Turtles all the way down. Someone famous said that. Okay. Yeah, this is you.
Yeah, that's me. So you guys read the title, so what we're trying to
Out of the way.
Okay, well, suit with the fork, retooling the Lime stack to embed an OpenFL app into a .NET control. So, like, why would we want to do that? First, some context. I'm David. Says so right there. And I'm kind of a just self-taught programmer. And about 14 years ago, I built some cardiology software as a standalone, and we were just testing it out at a facility. And once we started chopping it around, it became pretty evident that the way to actually make a living out of this was to actually embed it in other vendor software. So, so much for the executable for the standalone. So, got in contact with Alex here.
Hi.
And so,
Did you want more? Yeah. So basically, I came on board about 14 years ago, and helped him take this standalone Flash app and turn it into something that was marketable to giant software companies. Sell giant suites of software to hospitals who want to make one purchase decision instead of.
well, of course, we're big fans of Flash.
Yeah.
And so, co-founded a medical software company, Ionosoft, and we went to town, just trying to build the API, get everything working. So the current product is, as stated, it's basically a Swift engine embedded in a .NET control to be plopped in some vendor software. And so what it basically does is you go in for heart cath, you need a coronary tree diagram. And so the coronary tree diagram, the way that people used to do it was to use like a drawing that's supposed to be representational of everyone's coronary tree, which is like a drawing of an oak tree and saying all of these look like this. So we came up with something a bit more flexible. And so instead of the text having to just draw on pictures and then the actual clinician coming back later and making corrections before going to the reading room and dictating a report, we tried to change the whole workflow. So in VCR, everything is just like procedurally drawn, dynamic. You can add branches and different abrasions, change the dominance, which is whatever falls into the posterior.
Show off tortuosity.
You can do cool stuff like tortuosity. And then pull in various aberrations that might represent the patient's current state. So maybe they have 6% stenosis, mid-LAD. So everything is drawn in real time. While this is going on, the engine is looking at the the angle of attack and the angle of flow and kind of registering like, all right, well, this one's going to terminate over here, and this other branch is on this side of the lumen wall versus, say, being on this side. And I don't know if you noticed, but the name change, everything is dynamically named at runtime due to these different rules. So what this ends up doing is when you're all good and ready, just hit the report button instead of having to dictate anything.
And you'll notice that we are no longer in Flash here.
Right. Right. So then you get a natural language report, and your job's done as a cardiologist for that particular case. You can move on, go back, and talk to the patient. Talk to the patient with like our nice little drawing that's a lot easier to understand than, say, raw clinical imaging, and tell them what needs to happen as a result of their cath. And then I'm going to pop over to the config tab and let Alex talk.
Yeah, so we're not going to really change many configurations, but we have a rich API that we expose to our host application. So in this context, everything in this window and the tabs themselves are all host applications. So this would be provided by our customer. And we integrate in and provide a rich object structure and make the entire thing incredibly customizable. And so this is just an example of an interface that we use to create our demos to customers. And every single interaction that you make on this screen involves calls to the Flash player, to our running SWIF in the Flash player to change state so that it changes the behavior and the way things display. So yeah, that's it in a nutshell. We don't want to dwell too much on that because this is all about what we're doing right now. So we decided to move away from Flash for reasons that are probably obvious to everyone in this room, and decided that Haxe seemed to be the best option. And I'll do a really quick demo of where we've come so far in our efforts. What we have here,
It's a perfect form. Absolute parody.
so you'll, I'm sure, recognize Bunny Mark with a few little extra bells and whistles from Haxe UI.
Yeah, thanks for Ian of Haxe UI for busting out like a quick GUI, because I was like, I'm out of time. Can you do something?
Right. And so really quickly, we'll come back to this demo later, but you'll notice that as we're changing sliders here, you might notice that the colors are changing on the sidebar, and I can spin rotation, turn the bunnies, and you see the rotation slider and the Haxe UI also. Oops, too many
Murder bunnies.
Too many murdered bunnies.
The humanity.
So that's it in a nutshell, and we'll go into some of the rest of this stuff, tick rates and stop loop, and there'll be more context for that later. So basically, this is our architecture. We have an embedded app and we have a host app. And our current implementation, the embedded app interacts with the Flash player, the host app interacts with the .NET library, and there's a communications pipeline between them.
External interface.
Yes, for Flash, its external interface is all of our communications. Now, what we just demonstrated is sort of a conceptual replacement of the Flash player with OpenFL. And we're again communicating to the .NET library, not through external interface, because OpenFL does not support external interface, but through something that will eventually be an improvement of external interface. It's in its early stages now. We call it external COM. And it is, we'll go into more detail a little bit later on exactly how that works. And then another benefit of moving to Haxe is that software in hospitals moves very slowly, but it's not at a standstill. And large Windows desktop apps are not the future. So we would really love to be able to do this on our single code base. And instead of having a .NET library, have it be a JavaScript library and run the same OpenFL and still be able to deliver what we deliver. So, architectural constraints. Currently, we are limited to a Windows environment by our customers. Our customers expect us to deliver a .NET control. They expect it to run in both 32-bit Windows and 64-bit Windows environments, and they expect not to have to worry about anything other than put the files where we tell them to put the files, and here's the documented API. So we identified 3 challenges in retooling OpenFL and the Lime stack. Most of the work here is in Lime, to make what we want to do possible. There is the game loop, which is completely not a non-starter in our environment. So you have a tightly running loop that, in essence, this is the pseudocode for what it is as it currently exists. Application.exec runs, and it does a short initialization, and then it runs update. And update is get one event, process one event, repeat until no pending events, then wait 1 millisecond, and then run update again ad nauseum. It's an oversimplification, of course, but this is fundamentally the current state of Lime. So what we did was we created a new method that executes a batch update, and so unlike an update which gets one event, we fetch events in batches. They're provided by the SDL layer, if you ask nicely, and then we loop, processing one event at a time across this batch of events. So that's step 1 in a tool to work with. Step 2 is to break a init out of exec and expose it in parallel to batch update. And what we do is we do the initial simple initialization, and then we run a batch update for 20 events with the idea of, so events at initialization time, events tend to pile up. And so, we have mouse move events and whatnot. So we just process whatever happens to be there. 20 so far seems to be a more than sufficient number. And then, externally, periodically, in our case on a timer, we, from outside the application, from outside the OpenFL application, we call batch update. And currently we have it's tunable. Currently we're processing at most 10 events per tick. And so we have some flexibility on how frequently the ticks happen, and we have a lot of flexibility on how many events we attempt to process at maximum per tick. So now we're going to go into David's realm and talk about exactly what happens when an OpenFL app starts.
Right. We're working on both sides of the whole Lime stack here. So from front end, when everything gears up in an OpenFL app for a CPP target, then you're going to hit application main. And so had to make some edits to prevent it. Generally what happens is main gets called, and then it'll run create, which is a long set of everything from all the minor initializations to then it goes on and sets up some Windows attributes and meta and everything it needs. Spawns up some preloaders, and after the preloaders get done, they'll fire a start function, and then everything goes to, all right, we're ready to the loop. So it'll set up that blocking loop, and we got to pull out from that.
Right, and for the record, as soon as that loop exits, the whole application shuts down.
Yeah, so we got to pull out of that too.
Yeah, so that's the current state.
So made some modifications. So now create is pretty thin. It just sets up some meta, and then just waits for the other side to call. At that point, there's some methods exposed. You got good old create window, the standard that was always there, just shoveled into its own little function, callable. Does everything that would have been done in a natural OpenFL app. And then we pull create window from, expecting a foreign window handle. And this is where things get rather interesting. But from this perspective, we're just exposing that method and then calling Lime applications create window from, which doesn't exist yet. So
yeah, we'll get to that in a minute.
So what you're seeing here is largely replicated all the way down the stack to expose it from SDL layer all the way up to me. So all of that's pretty thin.
Yeah. So now we talk about window creation. So The second obstacle, aside from the game loop, is the fact that Lime and OpenFL expect to create a window from scratch in the native environment for the native target, own it for its entire life cycle, and then kill it when they're done. So that obviously is not going to work for us in our use case, because we have to start with a window that is hosted in a process that's owned by our customer and make OpenFL interact and play well with that window. So the current state of window creation, again, big oversimplification. Application.createWindow. You pass a bunch of window attributes in the form of flags, and some of those flags come from metadata and other places, and yeah. So oversimplification. And then there's a few layers of window constructors for different kinds of window classes. We're just going to simplify that with new window, bunch of attributes. Then we get to the CFFI transition. By the way, this was something that it took us a while to actually understand, as approaching the Lime library from an outsider's perspective. First of all, I had no idea that Lime even wrapped SDL when we started. Just complete no pre-knowledge. And then you're trying to trace the Haxe code and trace the generated C++ code, and you keep running into this massive monster called native CFFI.haxe. And so many conditional compilation constants, have no idea which of the many calls are being executed, don't know what prime means in this context. It's a farce. And we eventually pick out the trees and realize what exactly has to happen, and navigate this CFFI. Another thing that has to happen that we didn't realize that HaxeLib didn't give us the code for any of this. We actually had to go directly to the hub. We thought that we had all of the Lime code, and there wasn't even an empty directory to say, oh, you should have more here, which is the entire Lime in DLL source code.
Lots of forks, lots of clones,
right,
and lots of rebuilds.
Right. So once we get to the Lime in DLL, we have another create window passing a bunch of attributes, which resolves to essentially another constructor for an SDL window in the native target, of course. And then we get to the SDL big worker. This one does the heavy lifting here. And what create window does, what SDL create window does, is it compiles all the attributes that have been passed all the way down this stack. It then calls to the system. It makes system calls to create the window with the appropriate attributes. Then it does something that, if you're familiar with the nuts and bolts of OpenGL, which some of you may be, then it creates it finds the device context of this window, and by device context I mean memory area that is blittable, and then sets a pixel format, which is the most arcane and strange process. If you ever have the opportunity to look at the code of anything selecting a pixel format, I can only imagine how that evolved from 0 to now. So then, once the pixel format is selected, it then returns. So, in order to sort of retool this process for us, we found another very, very seldom used, its existence is seldom acknowledged SDL function called createWindowFrom. And unlike createWindow, which takes a lot of attributes and creates a window to tight specifications, createWindowFrom takes nothing but a void star, and then doesn't even make a window. the void star is interpreted as a window handle to a window that has an existing operating system window that has been passed to it. And then it goes and as you can see, so set up window data here. This is the actual. This is an abbreviated version of the actual SDL function. The meat of it is set up window data, which goes and extracts information from the operating system about the window and stores it in the structure that you see at the top there, the SDL window struct, which is the window variable. So the major oversight of this function is that if you create, in virtually all cases, if you create an SDL window using create window from, it will not have OpenGL support. No matter, you can set up the pixel format yourself, have a fine device context ready to go. The rule that SDL establishes is if a foreign window, which is what they call windows that have been passed in and not generated, they will not attempt to change anything at all under any circumstances about a foreign window. And that includes making any assumptions about whether or not it should support OpenGL. And there's no mechanism for you to tell SDL that this window should support OpenGL.
Despite some requests.
Yeah, so you can see my comment here. I made one line of code change to the SDL repository, and that is it. It is please support OpenGL for this window. All right. So, given where we came from, given where we've just gone, we had to do a refactor of the line calls. First of all, if you'll remember, on our way down this stack, most of the work was done in window object constructors, or so window class constructors. And that was assuming we were creating a window. So what we did was we pulled the actual window creation logic out of the constructor and put it into a create method. Made no other significant change other than that. So you'll see we now have an SDL window create instead of constructor. And then in parallel, we created a new class called SDL foreign window. And SDL foreign window inherits from SDL window. And it, in addition to everything that that's in the SDL window interface, it supports a create window from and takes a foreign handle. And you can see where this is going. There's a CFFI transition, so we gave create window from a nice little window in the CFFI layer. And then you see at the top, same thing. The window constructor is replaced by a window.create. And at the top level, the same window that has create exposes a create from. And at the very top layer, you have application.create window from handle, which is where David left off on his part from the OpenFL initialization template.
Which is application, and then it goes up to also OpenFL.
Yeah. And so this is an abbreviated version of the header file for SDL window, just to give you an idea of the sorts of things that SDL window supports. It's basically, tell me about this window, change something about this window. And it's basically a proxy for the operating system. So what we have done is we created the SDL foreign window as a subclass to support everything, but we have to maintain the rule that we can't attempt to change anything about the window. So you see all our overrides here with no ops. So we just extracted all of the operations that could dangerously change the window. And you'll see we have the create method is also a no-op in this case, and we've added a create from declaration. And create from in SDL foreign window is at the beginning it does what you think it does. As you can see, it calls SDL create window from, which is the function that we touched on before. Then down at the bottom, it attempts to load the operating system OpenGL functionality. That's what SDLGL load library does. And then it attempts to create a context, a render context in this case. If it successfully creates a render context, Then we do some more OpenGL bookkeeping. And then we check it at the end there. If after all of this we do not have a context, we initialize the software render. So now we're into external comm, which is the third sort of pillar of our tripod. Third leg. Tripods don't have pillars. It's the third leg of our tripod.
Greek tripod.
Yeah, it's a very, very Greek tripod. External comm is an API layer. I leaned on it. It's an API layer that we expose both on the .NET library side and also on the OpenFL side. That allows the encoding and decoding of function calls. And so it's essentially an RPC structure. And here's an example of version 0.1 of our JSON schema. Yeah, it's already changed a couple of times. Yeah. And for obvious reasons, like we didn't have time to build in array support for this talk, but it's coming, and we didn't have time to finish actually implementing return values. So our current calls don't return, but that's coming as well. But we have a data structure for the call and a data structure for the return. It should be pretty self-evident what's attempting to be done here.
Call ID in case you get lost.
Yeah, exactly. And then, so now on the OpenFL side, this is external comm.
All right, so external comm is, you can't really peep into external interface on Flash Player. It's buried in there, it's proprietary. So made some guesses as to functionality and just hacked out as quickly as I could something that would be functional. Where I have a series of different types in an enum, and let's see, you can see that I've got some type defs for just some of the schema that we're going to be passing back and forth. And external callback is that's what's necessary for beginning the pipeline. So Alex's end calls a method on me that will set the external callback so that we can begin and initialize our communication. And so call ID again is what if you have an async operation, you want to which return did this actually belong to? It's just handy for that.
And also we're thinking in terms of extensions for the use of that schema. Why not be an RPC where the communication layer is the network pipe and not just a function call? So there's definitely some synchronization that needs to be baked into it if we want to support that.
Right, you can see some laziness of that sort of extension in some of the type defs. So the external callback is it's going to be a callable for CPP. Otherwise, it's going to be a string for now. And same thing with string const char star. So, what do you need to do? You need to be able to pump, get the types from values and set values from types from this JSON schema. So a lot of boilerplate, but that would go through the type enum and go, okay, I think this particular value matches this one, so let's go and construct. This works pretty all the way down on this end of the external comm, where there is deep array support and some deep object support, and custom classes can still pump in and everything, and then convert back and parse back. So adding a callback, so that's kind of the same sort of principle that external interface would use, where we don't want you to necessarily go just calling willy-nilly. Here's a list, like a white list of callable functions. So that's what we use it for.
That's not.
Or adding callback for things that you call on me.
That's for you to call on the host application.
I will set up methods on the front, and that's mine.
Ah, okay, I see it.
Yeah.
My mistake.
Yeah.
Sorry.
So that's mine. So I'll just whitelist. I'll just whitelist as many methods that I want to have to allow access via external com, and remove them as necessary. And call internal is when on the previous screen on call function. Call function is just like the outward layer exposed all the way at the top, so that it'll just pump into my private method for call internal. And that's the simplification there is like, all right, well, that his end wants to call a method on my end. So let's go ahead and build the schemas necessary and run the method after I convert all the args and find the function name and make sure it's in the whitelist. Call external is just the inverse. So if my area wants to call back on him, that's the pipeline through there.
Okay, so in order to actually execute what we're doing, we had to go through a pretty awkward build process that we hope to streamline a bit in the future. The first like sort of real limitation and is that if you build a static lib target on OpenFL, it requires that it statically link to Lime. And at some point we'll go through and fix all the defines and figure out how to decouple that, because we'd really like to be able to have a static library as a build output from this OpenFL build, and still be able to in the end dynamically link to the Lime and DLL.
Yeah, we know where it lives. It's just a matter of a lot of tedium.
Yeah. And so for now, step one is to build a static libline in lieu of the NDLL, and then build a static OpenFL application linking to that static lib. Then, and this is what we're going to touch on next, is build a DLL from that application lib and a C++ source file that exports a small API. And then once we have that, we build a .NET library that consumes the API that's exposed by this DLL. So let's start with enginewrapper.cpp. In fact, actually, start with Lime wrapper. So in order to start running Lime code, if you're not doing it the default way, you have to know a little bit about what Lime expects at initialization, and so you can see some of this in our Haxe and Lime forward declarations. We have a forward declaration for HXCPP set top of stack, which is pretty important for garbage collecting and probably some other things. And then we have HX run library, which when that is run, then the application main that David illustrated in the template, that's that entry point. And then in order for Lime to run at all, you have to call some register primitive functions. And in our case, there's the basic Lime register prims, and then the prims for OpenGL and the Cairo software render.
Yeah, if you want like audio support or whatever, then you have to register those prims as well. Right. Anyone is at all interested in replicating into this at some point.
Yeah, right. Yeah, audio is not part of our use case, but yeah. So then we have here is a very tight, and the intention is for this header file to not change. So regardless of what kind of application and what kind of embedded application and what kind of host application, the intent is for this header file to be mostly the same, absent two little defines at the top. We have an object name where these statics are actually implemented, and a namespace for it. So this is our very limited API, and we accomplish everything that we do with this vocabulary. In fact, we don't even use all of it. Like app exec starts the game loop, and we don't do that. But the ability to do that is there. We can completely externally kick off a standard Lime event loop via this call. And we have here single update pass. This is my batch update function that I mentioned before, where you pass in the maximum number of events to process. And we have here our create window and our create window from, and the same thing. And the window side and the execution side can vary independently. So you can have you can have a timer external event polling with a Lime-owned window, and vice versa. You can have a standard Lime exec loop with a new foreign window that's hosted here. So, and this part of the source code is not that interesting. So another thing that, because it's all pretty much been defined there. We have an init Haxe, which has to be called first, and you'll recognize everything you see here. In fact, you can find essentially, it's give or take, this code in a lot of repositories around the net. And we have some boilerplate, essentially DLL exports, and then we have some stuff that we use to actually make the foreign window that's hosting Lime behave well. And so, and you know, we register a window class, and all this, it's arcane Windows stuff that's probably not very interesting and a lot of a headache. So the HXCPP config is a very important include for us. It's generated as a side effect of a native target Lime build, or a native target Haxe build, sorry, and it sets all the important defines that make everything work. So we include that, and yeah, and just to show you sort of the difference. This is our public interface. This is the file that we scraped it from. So you can see basically all of the C++ versions of the interface to the external API object that was defined in the OpenFL application. So then, oops, see where are we going next? Really quickly, here we are in Visual Studio in the world of C#, and there's really not that much to say over here. There is LimeHost and AppViewer are the most are two of the most important classes for managing the foreign window whose handle gets passed down to Lime. LimeHost it's actually LimeHost's window handle that gets passed, and everything, all the code in LimeHost has to do with making itself amenable to being used for that. So we have some window style things. We're overriding create params to set a custom window class, which was defined in the DLL. And then here, as soon as a window handle is created, we set up a pixel format so that we're enabling this window for OpenGL. And really quickly, so this is the arcane code for selecting pixel formats. It's a pain. And then it advertises that it is finished with its initialization. And now AppViewer is another control that hosts the LimeHost control. And so this is the one that actually gets plopped into the what you see is what you get editor for a .NET form. This one behaves well with the .NET world. whereas the Lime host one definitely does not. In fact, you can't even run most of its constructor in design mode. And so the only interesting code in AppViewer is everything to do with the timer. And so AppViewer is where the code that actually executes the event loop updates lives. So what we have here is we're setting up a low-level operating system timer in Windows. Setting the tick rate, telling it to start ticking, telling it to stop ticking. And you'll see here on the timer tick, if the engine is initialized, we call engine update on the Lime host, and that's what makes the magic happen. Not at all necessary to use C# for this set. In fact, most of the code I've written is badly mangled C# that would be much more comfortably written in C++. So it's all that's required is Windows at this point. And then we have our business logic, our bunny business logic, here in the bunny controller class. And this is where we interact in order to communicate with the embedded app. We use external comm so we use export function, which sends a callback to the OpenFL app so that when OpenFL wants to call one of our exported functions, they have a pointer to do so. We have call external function, which calls a function that is exposed by the OpenFL app. And then we have boilerplate. We have JSON encoding, decoding. Yeah, less interesting stuff here. It's just basically and then we get into here. So on call received is the callback. So this is the target that actually gets run by OpenFL code that makes an external comm call to the host. And so we parse the call, and then we dynamic invoke it. It's a function table, just in some arcane C#. So that's really what we have here. So let's go revisit our demo.
Now that we have a bit more context.
Yeah, and so you'll see that there are a few more controls here. Like we actually have the ability to stop the loop. And so the game loop is paused, and something kind of interesting is, so that's a click, that's a dead click, right? Well, when we start the loop, it's not a dead click anymore. It actually spawned. It's queued up and ready for processing when the event loop starts again.
Which could be handy.
Oh, there we go. Oops.
Which could be handy for making, like, for any adventures and maybe attempting to make like a frameless, a frameless version or something that just kicks off with events and then like, okay, click happened, now let's roll the OpenFL exec loop.
Sure. And so you'll notice what we have here in the title bar is a ticks per second measurement. And that's basically critiquing the efficiency of the timer that we're using to send update directives to the OpenFL. And we are limited by most modern CPUs allow the operating system to interact with them to control what kind of timer resolution you can have. And you'll find it sort of dynamically changing during runtime. And so that's a little bit annoying. But you can see that at a tick rate of about 35 ticks per second requested, we're getting a consistent 33 frames per second unless we start to do anything intensive. So you notice as I drag the mouse over, we lost a little bit of frame rate because we actually have to process those events. And this is our trade-off. So the standard OpenFL app owns the world and calls external libraries as necessary to execute its business logic. We've inverted that by necessity. We can't kill the running process of our customer. That's just a non-starter. So what we end up having to do is be a very good neighbor and drop our own performance. And so it also raises some interesting points that with this control, the ability to tick on demand, you could actually implement, you can actually like take ticks completely out, you can take frames completely out of the equation. And you can do a render on invalidate if what you have is just GUI and you don't have like animations that have to be smooth. And so you can gain a lot of CPU just from that kind of an optimization. And that's something we're considering. As a general rule, from our previous experience with the Flash application, as long as our frames per second is like 21 or more, that's about like the 50 millisecond latency between action and response. That's sort of the threshold where anything worse than that and the UI looks choppy. So we have a pretty modest frame rate requirement. But of course, we like better frame rates because it makes dragging and redrawing look smoother as we go.
Yeah, mileage may vary on any one of these machines.
Right. And so let's stop the loop and drop the tick rate here, and you can sort of see that the frames per second drops as the tick rate goes down. And so we're at a point here where it's just really, really, really difficult to manage. And so as we go up, so what's interesting is we were testing last night, and sometimes as we kick this tick rate up, the operating system decided we had like a 33 frames per second hard cap. But then some state would shift, and suddenly we were running at 61 frames per second. And that's purely because the operating system allowed us to have this timer resolution as high as we asked for it, as opposed to basically throttling us down. And so that's an interesting side effect that we weren't expecting that we're going to be able to work with, because again, at worst, we're getting throttled down to 33 frames per second. So that's perfectly fine for our uses. But let's just for the sake of argument, let's attempt a tick rate at 200 ticks per second. Okay, so we're up to 60 now.
So,
right, exactly. And so we'll be at 60 all the way down to probably about like in the 80s. I think we're still going to be at 60, right? Yeah.
So as we began this journey, I'm sure there was an awful lot of head scratching, and people who we've conversed with these marvelous 3 days, it's like, why would you do any of that? And I'm not sure that we've satisfied that yet for all of you. Time will tell, but I see a lot of different applications here. For one, just getting things like OpenFL and Lime and Haxe into .NET world. That's just not a thing that's really happening as far as I know. And we're finding out why on the way. So I think that's just like different demographic, different kind of needs, more maybe application space for the community. But there's also obviously things like the math editors or modularizing. Someone could maintain a DLL that is nothing but the GUI overlay for a game that's like really dialable in for customizing however you want your game, and you just don't have the time for it. You can just plop theirs into yours and just build these stacks of different OpenFL projects and throw them all into .NET or CPP world.
And with external COM, you can dynamically send objects in at initialization time, and have a lot more flexibility for for some runtime options.
None of this is perfect at all. In fact, it wasn't. We hadn't got it working yet until like about a week ago.
Yeah,
Before we-
4 days ago, maybe.
About 4 days ago.
5 days ago, yeah.
Yeah, and grab this, like in the thick of it while we were like, oh no, the flight's in a few days, and this was probably 3 days before we left. I woke up in the morning and my computer died, like motherboard out. So like trip to Best Buy and how quick can I get this back going? It's like we got a thing to do. So it's been an adventure for sure. So I guess now we can. I'll go ahead and say that like our visual
7
Cath-
minutes to spare. Wow.
our visual Cath reports tool does exist in an OpenFL port. It's just not really ready to show because we got to do like some client demos and everything first, and we've got some IP concerns. But it does exist. I guess now we'll take questions.
Sure. So I really appreciated you walking through all the obstacles you faced, and once you did it, that was pretty low level, but that was impressive that you powered through that. But it left me wondering, like, given that encryption is going to, and then SDL is definitely a thing, why there isn't a better first-class mechanism using Windows that should basically in the enterprise software world. Like, I see a problem like that, and I'm like, who should own that? Like, who's responsible for making that more of a first window rendering?
Yeah, so it's basically a question about owning the idea of sharing contexts and rendering across windows, and where does Inscription fit in? Those are great questions, and they seem to be kind of rhetorical. But I share like a strong interest in all of those answers, and hopefully we're gonna sort of muddle our way forward and hopefully contribute to some progress towards them.
It seemed like my hunch would be that SDL would benefit, so they would, probably the most, adding a workaround just for your sake.
Right. Yeah, I would think so.
So my SDL workaround, it's interesting because there are SDL forum posts going back to like 2014 where people are asking, and it's mostly people who are trying to make map editors using SDL. And there's like, please let me use OpenGL in my foreign window. I mean, just let me do it. Or here's some code for a hint that checks to see if I said that it's okay to make foreign windows OpenGL support, and if so, sets the flag, and there's just no move on it. There are some SDL forks where people have done this, but the impression that I get is that create foreign window is such an edge case that most people probably that most SDL maintainers probably have forgotten that it's. I mean, that's my guess.
But we'll have to maybe start a dialogue with those guys.
Yeah.
Yeah. And one other quick question: you talked about map editors. I'm not familiar with some of the other like shared components by arenas, but I know it's a big deal. Essentially, like car navigation system. A lot of opportunities. I guess like one other question would be: when you are running your system, medical software, what do you guys have to do to worry about privacy? Anything that like you have to, given that you're no longer kind of like an own app.
Right.
Like, is there like I mean, I guess I'm asking if there's any security concerns.
Well, we'll make measures to try to lock it down, but that's something that's like literally on the list of things to look into because we don't really know. Like one of the interesting things of moving from like Flash Player to like, all right, let's explore OpenFL and Lime and everything was like, well, So one of the reasons we're moving is like no one wants the security risk of like after they pull the plug, there's no more security updates. Well, like, does anyone check like this stack for the similar kind of expert? And I'd be really interested to know and maybe talk to some people about how we can get that going.
Right.
So like that's a space that I really don't know and I need to look more into and would love some help.
Okay.
And then when it comes also to like black boxing, like we as a rule never dealt with like patient data anyway in our application. It avoids us being like considered a medical device in the FDA, stuff like that. So we're black box from anything that we would be nervous about getting out in our specific case.
Yeah, in our application, we're essentially like a document editor from the perspective of the doctors. We're not doing anything with we're not persisting any patient data. We're basically Microsoft Word. You know, helping them generate
doing diagnostics.
helping them generate documents.
It was real slick. And one last question. Sorry
No.
But the original demo you had, is that all completely spline based or there's a constraint based thing?
I can't get too deep into that
Okay.
because I rolled some
Especially
of my
on the
own.
internet.
Yeah, that's long research, and I kind of rolled it all my own
Okay.
for kind of my proprietary, like, yeah. Yeah, absolutely, and that's part of the idea is to be able to be responsive, and so the next stage is a polling mechanism on some level to recognize that we're backing up, and it's worth it's worth dropping the processing rate in order to catch up. Right, like flexibility
Absolutely.
on it, that it actually stretches. You know?
Yeah. Yeah. Sure.
Did you think about, difference
Yeah. There.
We kind of almost did that once.
Yeah. It adds as many difficulties as it solves, perhaps more. Because you run into, the communication channels are not really easier. They're sort of the same. The overhead, like memory footprint on an already memory intensive application for like embedding Chromium is insane. No. Oh, sure. Oh yeah, something like that. Yeah, no, that is definitely a possibility. Definitely a possibility. Yeah. Mm-hmm. Oh yeah, of course.
Yeah.
Sure. No, there's a reason. So I don't know if most of you know or not, but external interface is just an XML RPC format. Mm-hmm. That's all external interface is. Mm-hmm. And so that was versioned a very long time ago and never touched. And we struggled against those limitations as well. And that's part of the reason that we wanted to break away a little bit from it. Yeah.
And our current schema is just like whatever it took to get this done.
Right. Yeah. Exactly.
And then we're going to go back to the drawing table,
Sure.
and
Yeah.
formalize everything.
We'll make some good engineering decisions later.
That should be our famous quote.
Yeah. Right.
All right. Anybody else?